Okay, hello everyone. Welcome back to the Topos Institute Colloquium. Today we're very happy to have Fosco Loregian talking to us about two-dimensional transducers. So please, Fosco.
Thank you, David. First of all, let me thank you and all the others for the invitation here. I'm very happy to participate to the Topos Colloquium. Then the second thing I should say at the beginning is you can stop me with questions whenever you feel you need clarifications. If you desire some more conceptual, some more longer detours, maybe it's better if we discuss at the end of the talk. But I'm very happy to receive all sorts of questions. So now let me start with the talk. The content of this talk comes from essentially in its entirety from a very recent preprint that I put on archive. So the title of the preprint is the same of this presentation, and it's essentially and it has the same abstract that you have probably seen in the preview of this colloquium issue. You can easily find this on archive if you Google my name and the title. And of course, I'm very happy to receive any comment you might have if you read the paper. So if I had to summarize the content of the paper in a few words, I would say that it is some category theoretic, some mathematical study, an attempt to a systematic study, even maybe a bit pedantic in some sense, of a certain concept that is very dear to people in theoretical computer science, which is called transducer. So people study these structures, but the category theoretic nature of them, it felt a bit elusive to me when I first learned about their existence. So my motivating question, my set of motivating questions was, well, I'm a category theorist. Some things come more natural to me. Some way of thinking about gadgets comes more natural to me in terms of category theory. So I would like to describe with the tools of category theory, in the language of category theory, these kind of gadgets. And of course, one would want whatever a transducer is, thinking that it's related to the field of automata theory, language theory and automata theory, one would like to interpret this gadget as some sort of process that can happen between an input and an output. So one would want to organize these objects as the morphisms of a category. And then the next question is, what are the categorical properties of this purported category of transducers? Then, if one wants to be a bit more aim a bit higher, what mathematics can you do when you have this category and you classify it and you study it in terms of categorical properties? What mathematics can you do in it? So the strategy that I like to apply here was similar to the Grothendieck analogy of submerging a nut in order to open it with time. Of course, with a little bit smaller scope than what Grothendieck did, but the idea that I wanted to use was to submerge this category into a bigger two categories, so studying a two categorical structure in order to understand whatever category transducers form in terms of the subcategories spanned by discrete objects, by whatever you get in two transducers when your objects are discrete categories, are sets. So people study these objects, and well, I can already spoil the final answer to what transducers are, because the paper essentially tries to make a point that a transducer is nothing but an instance or a generalization of the notion of profunctor. So all of the people present here know and love profunctors. They know that we all know that they can do a lot of interesting things. So my take on this matter is that a transducer should be interpreted as a generalized profunctor. I will be more precise about what generalized means in a few minutes. And well, in some sense, this is not a new idea, because people that think about these gadgets as processes. They imagine these as some sort of generalized relations. And we all know that relations are a decategorification, or rather profunctors are a categorification of relations. So my aim is to make this precise and explain how close one is to manipulating a profunctor when they study a transducer. So how much more, in what sense they are more general, and what intuition I know I have on profunctors I can use to understand and classify these objects. So my way of seeing this business of automata theory and formal language theory is very rooted in representation theory. For me, these objects are just actions of monoids that happen to be free. So can I use this intuition, which again is not mine, it's a very common way of seeing these gadgets, in order to find some compelling analogy between profunctors as representations, as modules, and transducers. So these are the motivating questions. Now, I should also spend a couple of words saying that this piece of work is embedded in a bigger setting, in a bigger picture. It has been a while since I started studying this field of computer science, that is automata theory, trying to reenact a pretty old line of research in category theory that tries to use formal category theory as a foundation for for the theory of automata, or the theory of processes. A bit more context may be needed in order to understand my take on the matter, and also what to expect from this talk. In few words, I come from category theory. I am a category theorist, so I will have that kind of perspective on things. In a few words, I can also I can spend a couple of words on where these come from, what my motivations are. Some of you might know that I work in the group of Paweł Subocinski in Tallinn University of Technology. So some time ago, Paweł came to my office and essentially told me, it is a good idea if you start looking into the use of category theory in automata theory, because it's probably a fun and interesting task. You might find something interesting to do. And also because, you know, the grant who's about to pay you is about that. So I don't consider myself a particularly sharp or particularly fast mathematician, but I think I am very good at what is called malicious compliance. If you tell me you have to study topic X, I will certainly find a way to keep doing category theory while pretending to do, say, topic X. And also along the way put some category theory in it, of course. But my preferred point of observation for mathematics is category theory. So I'm not moving from there. So I said, okay, I have heard and I have talked with people that essentially try to push the idea that formal category theory, as abstract as it might seem, has something to do with the theory of automata, with very applied, if you want, a very discrete and concrete part of computer science. So I know, sort of, I'm not an expert, I don't consider myself an expert, but I love formal category theory. I think it's a very elegant way to do category theory. So I wanted to know more. And well, my plan was I can do the latter, formal category theory, and try to sell my work as automata theory. So I am very happy to know what my abstract findings are about. I'm very happy to know if you have an idea to how to put a little bit more down to earth these concepts, these findings, these categorical characterization, but that is not where I'm an expert. So I will not pretend that I know more than I do really know. So with this idea in the back of my head, I started reading, and well, you will see a couple of references now, and you will also see that they are important pieces of category theory, although they were motivated by application to automata theory. So For example, there is this very old and partially unknown paper by René Guitart, From Automata to Bimodules. Unfortunately, it's a bit small and it was written with a typewriter. So this is a scan of a copy of a copy of a copy, where you see the keywords are lax coends in the vibrations, bimodules, which is, the old name for profunctor. Then there's this very beautiful paper by Bob Paré, which in the title contains the notion of a millymorphism, but not so secretly, is about enriched category theories and enriched profunctors. Then Guitart, which by the way was a student of Charles Erzman, had many of his papers were the initial input for this line of work. So then there is Stefano Casangian and Bob Rosenberg. Stefano Casangian again with Renato Betti. Some people know, but not everybody knows. I have noticed that the notion of enrichment in a bicategory, which is a very abstract, as you know, part of generalization of enriched category theory of the notion of enrichment, was devised by Walters with an application to these applied problems in mind. And indeed, Bob Walters was another, the work of Bob Walters was another propelling force for starting this line of work. So you see these last little bit shaded papers are the output of this line of work that I have done with two people that now ended up being my PhD students, and with other people that I involved during the last couple of years. So you see a lot of references, a lot of work. And well, now let me sketch in a single slide what I'm about to tell you about the mathematics. First of all, I would like to convey some intuition on the notion of transducer. Then I would like to show you how to organize transducers in a bicategory, or better, in a double category, because for many reasons, the categorical properties of these transducers are easier to appreciate when you study the double category. The language of double categories is also a bit more elegant. It's less cumbersome. There's less coherence in the diagrams to keep track of. I will sketch what kind of limits and colimits you have in this double category. And then I will show you a couple of things that you can do. And I had to remove many other interesting ideas from the paper, but I invite you to read the paper in the interest of time. I had to avoid mentioning them, but you can easily find the paper. So I can easily give you the definition immediately. A two transducer is, mathematically speaking, a pair made of a category, Q, that I will refer to as the category of states, and then a functor, T, with type A times Q opposite times Q into the presheaves over this B star, where B star is the free monoidal category on B. And now you would like to think of these with A and B fixed as an object of a norm category from A domain to B codomain. And in particular, if A, B, and Q are discrete categories, I would like to see people that study transducers see them as functions of type a set, Cartesian product, a set of states times the same set of states into the power set of the free monoid on B. So you see that linking these two lines, it's an evident, there is an evident process of categorification. And the first line is evidently something profunctorial, because it's a profunctor on Q, then decorated on one side with A and on the other with B. So, but first, before we get to that point, the intuition that I would like to have about this, that people have, that I wanted to maintain on this concept, is that of a translator. A transducer is some device that takes a word in an alphabet in a language A, like in Arabic, and translates, acting on a set of states, that word providing an output that is, or in this case, in this non-deterministic case, a set of possible outputs in another alphabet, which is B for Bengali. So more algebraically, but this definition is evidently equivalent, this kind of map can be thought of as a representation of the free monoid on A, so the lists on the letters given by the alphabet A, into, well, into some sort of ring of matrices where Q determines the side of the matrix and the coefficients are valued in this power set of B star. Now, you certainly know that profunctors can be thought as matrices, so the stretch as seeing this as a representation in terms of classical matrix theory is not that far, not that big of a leap. Maybe I should say that the coefficients can really be interpreted as a ring, or more precisely as a semi-ring, because the construction that takes B, a set, and produces the power set of the free monoid on B has the universal property of the free quantile on B. Now, a quantile is a monoidally closed poset. People study for all sorts of reasons these structures. So you see, from the category theory point of view, something really natural is happening that has to do with free co-completions, with profunctors, etc. So I would like to make this precise. A little example of this this kind of structure can be easily constructed. You can take an alphabet with 2 letters, an alphabet B with 1 letter, and then you want to act on a set of states, let's say with 2 states, specifying matrices, in this case 2 by 2 matrices, that basically generate a directed graph that represents the dynamic of the representation, where you essentially draw an edge anytime that you can pass using a transformation from an initial state Q to a final state Q prime. And then you decorate this directed graph with a pair, IF, where, or I is a typo, should be A, where A is the letter in the input alphabet, and F is a certain function in the power set of B star, in the free quantile over B star. Whenever the matrix element at place QQ prime for the matrix TA equals F. So if you write down in this, wait, where did the matrices went? Go. Okay, I lost a little piece of presentation. There should have been a matrix representing these transitions. Never mind. So it is relatively clear how to interpret a diagram like this as a elementary categorical notion. Now, the meaning of this diagram, now that I don't have the matrix to help me, is that in the matrix TA, there is in place 1, 1, there is a 1. In place 2, 2, there is x plus x squared, etc., etc. In place 1, 2 for the matrix TB, there is an x, etc., etc. So when you have such a directed graph, well, you may wonder, what is this gadget categorically? Now, you have a representation of a free monoid, and now it is very well known that representations of monoids, in particular of free monoids, are functors, in this case co-presheaves, over the one object category generated by the monoid. So if you turn this presheaf, this co-presheaf, into an op vibration using the Grothendieck construction, well, you get a category, ET. And it's a general fact, it's very easy to prove that since the codomain of this op vibration is a free category, so has to be ET, and ET has to be the free category on the graph that I was depicting before. So, but this is not all the structure that the graph that I was depicting before has, because the universal property of free monoids says that you have an extension from the alphabet, from the generating graph of the category ET, to the free monoid on the domain of the transducer. So you can associate matrices also to lists of words in the alphabet. And this, of course, means that you compose with themselves the edges of the graph to understand how they are, and to understand how they are decorated, you essentially perform a matrix product between suitable matrix elements. And so all the additional edges that appear in the free category are also decorated, or rather, I should say they are graded. The result will not just be a category lying over the monoid, but it will be a graded category. And grading plays a role in the general abstract descriptions of these gadgets. So you see that the new edges that appear are graded exactly by the matrix elements that you get when you suitably multiply the matrices TB and TA. So this is essentially what I just said. Now, this is the picture we would like to categorify everything I said. If a transducer is a function of this type, well, and occurring and extending to A star, a function of this type gives a representation of A star in matrices, then there are parameters on these constructions that we can wonder what categorify into. A
Sorry,
transducer is a function.
Fosco,
Yes.
Fosco, can
Yes.
I just ask for clarification?
Sure.
The idea
Yes.
is that we give some string of A's, and then the possibilities for B are is the power set of B star. The possibilities
Yes.
for what we can get out, and those
Yes.
are somehow determined by the state that we're in when we receive that A. And that's what you've
Uh,
talked about so far. Is
yes.
that about everything you
Yes.
said? And that you
Yes.
okay. Okay,
Yes. Exactly.
great, thank you.
So you're welcome. Of course, I'm happy to clarify. So this definition contains parameters that we can wonder how to categorify. In particular, I would like to categorify the fact that a transducer is a function, the construction that produces the free monoid, and the notion of matrix. And all these things rely on notions that I have already sneaked into the discussion. So I hope that the next slide, which contains this very same box, gray box, just categorified, will be transparent. So a two transducer is a functor of type, just uncurried with respect to the definition that I already showed you, but it's exactly a functor of type A times Q opposite times Q into presheaves over B star. Now, B star now is the free monoidal category on the category B, not the free monoid on a set anymore. But when a category is discrete, the free monoidal category and the free monoid construction coincide. So I should also spend a couple of words on what is really the category of presheaves over B star, because you can really think of it as some sort of categorification of a ring, or better, a semi-ring of formal power series. In the language of another paper and another line of work that I have been expanding through the past couple of years, I would like to call the presheave category over B star the free co-complete 2 rig over B. And then basically a two transducer consists of a representation of A star into the monoidal category of profunctors on Q enriched over such free co-complete 2 rig. So you see there are a lot of parameters, a lot of structure, a lot of words that play a role in this construction. The category that these gadgets form is pretty rich, you can imagine, if you think about how many parts of the definition can change or define a transducer. So one can define a bicategory where objects are small categories. One cells are the transducers that I just defined, and two cells are very straightforward to define. If you want to connect T and T prime, You specify a functor between the categories of states, and then a natural transformation that suitably fills a commutative triangle. So in this sense, one should really think transducer to form a category of generalized profunctors that are generalized in two directions. First of all, a transducer is a profunctor that is indexed over the domain because it's a family of profunctors on Q indexed by the category A, and you have as many as the category A prescribes with its objects and morphisms. And then they are also generalized in the sense that they are enriched over the codomain, or rather over a monoidal category universally obtained from the codomain. So I think it's an interesting notion because usually one considers profunctors that are enriched, certainly, but always over the same base. Instead, here, not only you consider profunctors enriched between different bases, but the base of enrichment and the base of indexing kind of can take the same role, because now in a moment I will compose one cells and I will blur the distinction between indexing and enrichment. So composition happens essentially as in profunctors. You just have to extend the leftmost composant not only to the presheave category, but the free to rig category. So you first take lowercase t and you extend it to B star, and then you take a left can extension along Yoneda to extend it to the presheaves over B star. Just for the sake of finding a name, I wanted to call this the Loran-Yoneda extension, because you first extend to power series and then to presheaves, but this is just a name. Observe also that composition by definition is graded, because composing two profunctors in defined over Q, one, and over P, the other, provides a profunctor in the over the product category, P times Q. The identity for this operation is, of course, given by the pair terminal category, 1, and then the ohm functor, the identity profunctor of A star. One can easily check that this definition gives up to ISO, up to a canonical unit, or the identity of composition. One can easily, it's just a very big diagram, write how whiskering works. I don't want to spend a lot of words into this technical specifications. I just want to show you that it can be done. It's not that difficult. You just have to keep track of how composition works, because you have to take the appropriate can extension, you have to induce the appropriate cell, but it's all a very straightforward exercise. So you can whisker on both sides. And yeah, similarly to what happens in the bicategory of profunctors, you can easily see that every composition left on the left or on the right is colimit preserving. So one might wonder whether there are right adjoints to pre and post composition, or in slightly more abstract lingo, if you have right extensions and right liftings in this bicategory. Again, you can easily see, using a little bit of, there are possibly many ways to prove this, one more conceptual, one more computational, but you can easily prove that there is a bijection for a suitable choice of these cell T/R that produces, in this case, the right liftings along a given transducer T. Reasoning in a similar way, one easily proves the existence of right extensions. And as a corollary of the fact that you have this bicategory, which is so well behaved, you deduce that there is a bicategory spanned by two transducers between sets, between discrete categories. So now the objects are sets. One cells are exactly the transducers as I defined them a moment ago. And two cells are functions between the carriers, such that there is a pointwise inequality between domain and codomain that now are valued in 2, which in this case is the semi-ring of Booleans. with its obvious order. So now that I have a bicategory, a two category, I can wonder, how does it work? How does it behave? What does it contain? Is it complete, co-complete, for example? And in order to do this, I found more natural to embed the bicategory into a double category, of which the bicategory that I just defined is the uh, is span in the double category. Two transducers, as I defined them before, are the bicategory of loose morphisms. So now a little bit more general definition. The double category of two transducers has, again, objects, small categories. In the tight direction, you just take functors. In the loose direction, you take two transducers as defined before. And cells with frame like this consist simply of pairs um, of a functor between the categories of states and a natural transformation that feels the very same to cell, just now taking into account the presence of F and G. If F and G are identities, you clearly obtain exactly the bicategory that I defined a moment ago. Now, the existence of limits and colimits, I don't think it's very enlightening. So let me just list what happens. You can easily prove that limits exist in this double category because they exist in the double category of profunctors. It's literally the same construction. Colimits are a little bit more complicated to construct, but you can still recycle the idea that produced them in the double category of profunctors. The first, well, if you want a general principle that helps in building these limits and colimits, you basically have to say, well, limits and colimits in the double category of profunctors exist in a certain sense with a certain recipe, and now the recipe that builds these limits and colimits in prof is compatible enough with the construction that takes a category and produces the free to rig, the presheaves over the free monoidal category on B, in the sense that there are compatibilities, natural transformations between, for example, the free to rig on a product and the product of all the free to rigs, etc., etc. One interesting point, because it's an obstruction to the existence of a certain limit, is for the non-existence of all tabulators. So the limits that do not exist in this double category are some genuinely double limits. Let me remind you in a couple of words what tabulators are. If you have never seen the definition, the universal property that defines them is that every cell, like on the left, where when I don't draw the horizontal upper arrow, I mean that here there is the identity of X, has to factor uniquely through a universal cell that you call the identity of which you call the tabulator of T. Now, if you write down this definition, if you work out what this means, a cell like Q and chi must be able to choose to point an object of Q. But the moment you have to point a certain category and you have to do it universally, then it means that that category must have a single object. So initially you might wonder, well, maybe there is another piece of the universal property that implies the Q is trivial, is the terminal category. But in fact, if you try to prove that the tabulator exists for a monoid, for a one object category, you manage to recycle the same construction in prof, which I find this an interesting fact, because if you keep looking at the category of one transducers, where A, B, and Q are sets, you don't really see that there is this phenomenon, because TDX one transducers doesn't have tabulators, because a category cannot be discrete and have more than one it cannot be a monoid. Well, a category cannot have more than one object without I I turn myself. I turn the words on myself. Sorry. You can't have tabulators in the by category of transducers, uh, precisely because now the categories are discrete. If you have a single object and you are uh, discrete, you must be the point. This is what I wanted to say. Sorry. So now that I sketched a little bit how limits and colimits work, let me tell you something more interesting with that has a more representation theoretic taste, a more representation theoretic feel. One thing that I find interesting is that you can really think of profunctors as matrices, of course, but you can think in a little bit more compelling way of transducers as some categorifications of linear operators in a suitable sense. And in order to understand this, you have to look at the Ohm categories between small objects, between categories, the empty category, the terminal category, the walking arrow, etc. So it is a general rule when one studied categories like this that Ohm categories between tiny objects have some combinatorial cute description. And the by category in study here makes no exception. So for example, all Ohm categories of transducers between empty and empty, one and empty, one and one are interesting and interact with each other. And in my view, they extend a little bit the perspective that regards profunctors as matrices. So if you want a little exercise, a small riddle to take home, I will do these computations for the empty and the terminal category. You can have fun characterizing the immediately more complex level in the ladder, which is two transducers out of the generic arrow, the poset 0 less or equal than 1. So if you open the definition of what a transducer 1 to 0 is, you quickly notice that it consists of a pair of a category of states, and then T, the profunctor, has to have this type. So now, what is the free to rig on the empty category? Well, it has to be the presheaves over the free monoidal category over the empty category. The free monoidal category on empty is terminal, and the presheaves over the terminal object are sets. It has to extend to the free monoidal category on the point, and in fact to its presheaves. So if you take this two-step extension, you get a functor of type set slice over n, which is the free to rig over 1, times q opposite times q into set. And this really is some matrix-like kind of structure, because if you see where an n-graded set times a couple of states has to go, the universal property of CAN extensions gives you precisely this formula. So if you don't see linear algebra here, well, my suggestion is to compare this with and build an analogy with the fact that if I give you a linear operator on a vector space, then I can use that, I can see that as a representation of the polynomials on one indeterminate. Where you act on a polynomial, the action on a polynomial is prescribed, sorry, there is a small typo here, this I should be an n. The action on a polynomial is prescribed sending g to the sum, the linear combination of the powers of the operator. This is a very classical fact that, by the way, packages in a very neat way the theory of Jordan forms of matrices. So the next step is to study transducers from the point to the point. If you, of course, as always, endo transformations must form a monoidal category. It must be monoidal with respect to composition. And the category L above is a module for this monoidal category. Again, if you open the definition, you see that a two transducer 1-to-1 must be just a profunctor enriched over n-graded sets. And its action on a profunctor like the one above is this cute way of mixing together the action of a family of graded sets and the iterates of another profunctor, of another matrix. Two transducers empty to empty is easily classified, easily understood as the category where objects are pairs, a category, and the Ohm functor on that category. I'll give you these as another little exercise in negative thinking. It is interesting that even if the domain and codomain are empty, you get something that is simple to describe, but still not trivial, not completely trivial. In light of this small result, it's also interesting to study how composition works. Because if I give you something empty to one and something one to empty, the composition must be the Ohm functor of a category. But which one? Well, if you try to do the computation and you open up again the CAN extension, you split it as a coproduct, you obtain that this category is the product of two categories of states, but not exactly Q and P, which are the state categories you start from, but instead Q and the category that you obtain taking T in its nature of endoprofunctor, the free promonad on T, which gives rise to a category, a free category, where the elements of Txy define heteromorphisms that now you compose freely. And then this P sub T star is essentially the Kleisli category of this promonad, which provides you with an interpretation for these freely composed heteromorphisms. So undeniably, this is a bit of a mysterious finding. So what is the nature of this? Well, if I had to push the analogy with linear algebra as much as I could, I would say, well, you can consider, first of all, given a field, you can consider the infinite countable product of the field times itself a countable number of times. And then you can consider this as a K-algebra. And then if you have a linear operator on a vector space and a family, a countable family of linear operators on another finite dimensional, let's say, vector space, you can regard these two as matrices. One is just a matrix n times n into the field, and the other, the family, is a matrix m times m into this power of k by n. And I don't know if this operation has a name or an application for that matter, but you can certainly consider a linear operator on the tensor product of V and W that is defined in a similar way. So I'm happy to see if anyone has a better interpretation or a use for this construction that seems very natural. I tried to find a little bit in the literature, but couldn't. But yeah, if you look at the PQ, P prime, Q prime element in the matrix that describes this operator on the tensor product, you find exactly a similar formula, mutatis mutandis. So last, and then I will wrap up, monads in the double category of transducers seem to be an interesting gadget. Of course, we know that loose monads in the double category of profunctors are essentially categories. And if you unwind the definition of a loose monad in the double category of transducers, you essentially get a category and an endo cell that is specified by a category of states Q and a functor of this type, A times Q opposite times Q, A star opposite into set. Now, the monad axioms equip Q with a monoidal structure. This is very easy to find if you open up the type of the multiplication and the unit. And then for every choice of Q and Q prime in the category of states, you have a promonad. So you have a way that is parametric in the states to add heteromorphisms to A star. It's a very rich kind of gadget, especially because all these data are specified compatibly with a grading. Remember that Q is monoidal, so composition now happens in a graded way. If you have an arrow x to y that is graded by a pair, let's say hk, and you have an arrow y to z that is graded by u and v, then the result of the multiplication is something x to z, of course, which is graded by the product of u and h and v and k. So this is some sort of graded category. This is some sort of graded multi-category, probably, because the domain of the functor is A star. It bears some relation with multi-categories that can be seen as monads. I didn't expand this very much for reasons of space in the paper, but I think the emergence of graded categories here is an interesting finding, especially because people in automata theory have studied graded category, graded monad. So finding a graded monad here, simply enacting, the monad axioms on a category where your processes are organized is interesting. It feels a bit serendipitous. So now, if I have enough time, I don't know how much, yeah. There are other models for study. There are other two categories where one can do automata theory that have been established in the last years, in the last decades. A natural question is to compare these bicategory or double category with these pre-existing models. One of the most famous of these is what is called the bicategory of circuits or processes that was defined by Katis, Sabadini, and Bob Walters. Essentially, their idea is to put non-deterministic a generalized class of non-deterministic Mealy automata in a bicategory of which these automata are one cells. So it's really the root of all these ideas that I have been putting forward. In the interest of time, let me glimpse a little bit quick over the definition. You essentially can read a very neat definition in the paper by Walters by categories of processes. So there is this category where one cells, this bicategory where one cells are Mealy automata, essentially, where a one cell A to B can be presented as this sort of a span where one leg is a dynamical system, a representation of A star, and the other is an output function, and then two cells are morphisms between state spaces that are these X. And it's relatively simple to build a functor that compares, that embeds this bicategory of Walters into two transducers. The idea is essentially based on seeing the morphisms, the one cells of Mealy cat as functors, so to speak, embedded into transducers in the same way you embed functors in profunctors. And of course, the category of states will be the category of states of the Mealy automaton. One interesting finding from the mathematical standpoint is that you can embed cat in this bicategory of Mealy automata with a functor, with a two-functor J, with a pseudo-functor J, which is not, that doesn't exhibit Mealy cat as a prior equipment for cat. You can embed Mealy cat in transducers with a functor G that is not a prior equipment, but if you compose them, then all of a sudden, the things that do not have a conjoint here and the things that do not have a conjoint here happen to have a conjoint when you compose G and J. So the intuition behind this is that the property of having a conjoint in transducers is made of two parts. If I embed something here in transducers with G, I resolve part of the issue, half of the issue, but I have to additionally restrict to the things here that come from a category in order for them to have a conjoint here. So I think it
Fosco,
is, yes,
you are now breaking into your question time. Just wanted to let you know.
yes. Okay, time to wrap up. So let me skip over this. Let me just mention one idea for future work. You can build these fancy objects. So one thing that I find interesting is related to a problem that I have been studying for a while already, which is some language for categorifying differential equations. And it's related to this problem because it's related to a pretty deep part of the theory of differential equations. Now, to cut it very shortly, people in differential equations study differential systems made by the derivative of a vector of, say, differentiable functions equals AZ, AY, where A is a matrix of power series. Now, this is a difficult problem in differential equations theory. It's easy, it's tempting to say that one can study a categorified analog of such a difficult problem passing to some to category that resembles transducers and makes them more refined in two ways. First of all, one has to take into account symmetric monoidal categories, and then one has to work in a setting where derivations make sense. So the most natural setting to do so is to study categories of species, since the work of 𝒬ᵒ, who introduces combinatorial species, we know that in this category there is a functor that works as a categorified derivative. So if you try to make sense of a differential system like the one above with a matrix of holomorphic functions, well, you essentially have to take a species enriched over certain symmetric, the presheaves of a symmetric monoidal category, and then you can probably make sense of an equation like derivative of y isomorphic to a tensor y if derivative of y is really the derivative of species and the product of matrix and vector is really the product of a profunctor, the composition of a profunctor and the given vector. So I don't know where this goes. This is just speculation at the moment, but I think it's an exciting research direction. Let me show you very quickly in a minute a couple of references. Absolutely non-exhaustive list of references, just because these are the works that I have been citing or using to take these definitions. And yeah, thank you for your time.
Thanks, Fosco. So we have time for a few questions. If you have a question, you can raise your hand using the React button, or you could just unmute yourself and ask. Let's see. No questions appearing yet. I was wondering if you have an interpretation. So I kind of interrupted and asked about this interpretation of, the set of possible next states and the set of possible outputs given an input A and stuff like that. Do you have an interpretation? I mean, the free monoidal category on B, I guess, is some kind of Petri nets where you allow yourself also morphisms from B, or something to that effect. But do you have a sense of how to say the word Petri net or whatever in a description of these two transducers? Or how to think about the automata theory friendly version of what it's saying?
No, I don't know. I think a relation might exist, but I think the construction that underlies a Petri net is essentially different from this because the kind of free construction to me feels very different because in order to build a Petri net, you take a monoidal signature and then you take the free monoidal category on that signature. I'm
Mm-hmm.
taking
A good point.
a
Yeah, yeah, you're right. But can you say any kind of transducer friendly language around what a true transducer is, or any kind of automata friendly um, language?
well, yes. Mm, I have to be sketchy, but
Hmm.
I can say a couple of words. If you look at this span, an exactly equivalent way to see this span is as a map into x times b, right? So
Yeah, this
this
part
is
I'm fine
this.
with. I'm more thinking about these q op times q, a times q op times q to presheaves on b star.
Yes. Now imagine that a, x, and b are categories.
Hmm.
Apply the same construction, but now instead of k equals set, k equal cut. Now a transducer is exactly a profunctor a times x into x times b. It's precisely that.
Hmm.
So
Hmm.
it's some sort of profunctorial take on Walter's construction of Mealy automata as these kind of intertwiners between AX and XB. And this is the entire reason why this functor G exists. It does exactly what I said. It takes a functor AX in XB and regards it as a profunctor. So this is the reason why this is half of
Hmm.
from being a prior equipment.
Hmm. Okay. Looks like Kevin has a question. Kevin?
Sure. Hey, Fosco.
Hi.
Maybe I'll give you two. Take answer at least one as you like. I'm curious that this might be fun. I'm curious about the double bracket notation. You've got some kind of Laurent series in your head, and I didn't quite follow the inspiration there, but it sounds amusing. And alternatively, so I can kind of get the motivation for one transducers and believe that some computer scientists think this is cool. They're sort of translators or something, non-deterministic translators. And then so you gave the double category of two transducers and some nice properties of it and some functors relating it. I mean, do you have any actual specific two transducers that you think are interesting that exemplify the theory, or it's all motivated from the global picture?
Mostly motivated by the global picture, I found particularly nice to play with these small examples. What is a
Right.
transducer one-to-one, empty to empty, walking arrow to walking arrow? The free monoidal category, or rather the presheaves over the free monoidal category on the generic arrow, is not difficult to describe, but you have to do a little bit of work because you have to think now objects are lists of zeros and one, and the morphism is some inequality between lists of equal length. So exactly what this category is takes a couple of paragraphs to write down.
Mhm.
So even staying at the low level, I think there is something interesting to find something very combinatorial, very concrete. Also, one can play with bases of enrichment that are not set. For reasons, I focus only on set functors, but one can rewrite everything for enriched profunctors, replacing set with a generic V.
Mhm.
So that's a tamer setting in which one can find um, like David has a wonderful, a very elegant use of profunctors enriched over a quantile in his 7 sketches. So there is hope that one can find very concrete, very, down to earth gadgets to tinker with if passing down to a poset based on enrichment or small finite categories of states. I hope, at least.
Sure. Thank you.
Thanks to you.
Okay, well, looks like we're at the hour, so why don't we thank Fosco again? And
Thank you.
we'll stop the recording and the live stream. And sometimes people stay on. Let's see, one last thing. There we go. Okay,
Can
yep.
I
So
stop
we are now.
sharing?